All right, in this screencast, we're going to talk about ocean currents. And I love this diagram. Okay, so this diagram was put together by the findings of none other than the very famous American founding father, Benjamin Franklin. And here's what Benjamin Franklin noticed. He was the first person to suggest the existence of ocean currents, which everybody thought he was insane. But he used to do a lot of trips between the Americas and Europe in order to try to win over the French to try to help us get our independence from England. Well, anyway, what he noticed is this. Some sea captains took a more or less straight across route. And when that happened, he noticed it, even though it was a shorter route, it took longer. And the weather was often more clear. But sometimes what he found was that the sea captains who made the best time, what they tended to do is they tended to hug the coastline of North America for quite a ways, all the way up to Newfoundland, and then cross over. And he noticed that the water was the air was often very foggy, and it occurred to him to bring a thermometer with him one time. It's a long trip; he gets bored, right? So he just took temperature readings. I mean, he was a true scientist, and what he noticed was the water started out warm, and then it got cold with the captains who went this way. But with the captains went this way, it got warm and it stayed warm all the way across. So he suggested, you know what, there's probably the reason we got there faster is there must be this warm water current flowing across the Atlantic Ocean from west to east in a clockwise pattern. And he called it the Gulf Stream because it seemed to be originating down near the Gulf of Mexico. So turns out ocean currents are very much a real thing. Thank you, Benjamin Franklin. You were absolutely right about that. And these continuous movement of seawater around the globe are driven in large part by the prevailing winds that are associated with the Hadley cell, which makes the trade winds, and with the Faro or mid-latitude cell, which makes the westerlies. And because of this, remember that there's friction between the wind and the water tends to get dragged along with the winds. So it's worth pointing out right now that these movements of water, these ocean currents, they are among the most important abiotic factors on the planet because what they essentially do is, remember, water has a very high specific heat capacity. It absorbs most of the energy that arrives on Earth. And so when you move this water, you are moving energy from the equator up towards the higher latitudes. And in doing that, you're basically you're affecting the movement of nutrients. You're affecting the weather patterns all over the planet because warm water evaporates and it convects, and so that makes wind patterns. And so much of the planet's climate and nutrient distribution is associated with these ocean currents. They're really, really important to the stability of our ecosystems. Now, the easiest way to think of this, and listen, they are very complicated. I'm not going to lie to you. They are complicated. We're not going to get complicated. We're going to keep it simple, which means we're just going to tell part of the truth. So here's the basic idea. Remember, in the between 20 degrees and the equator, we have the trade winds, and the trade winds blow from east to west on either side of the equator. What happens is they drag this water with them, setting up these equatorial currents. There's the North Equatorial Current and the South Equatorial Current. We'll ignore the countercurrent, but it's really kind of cool. The reason there's a countercurrent in between them is because, especially the Pacific Ocean, is the western side of the oceans are higher because of these winds, right? And so in between these two weather systems, where there's no wind that blows, remember there's that dead zone at the equator, so water basically flows downhill. Pretty cool. But that's not the one we're going to focus on. We're going to focus on the equatorial currents. And these basically are taking warm water. Remember, warm water floats to the surface. It's less dense, so it floats. So that surface water is very warm. It's been heated by that equatorial sun, and it's being dragged across the ocean in this fairly fast-moving equatorial currents. Now, when these equatorial currents reach a landmass, they get deflected. And when they get deflected, the Coriolis effect comes into play. And what happens is they end up getting deflected in such a way that in the northern hemisphere, they're going to tend to go in a clockwise pattern, and in the southern hemisphere, they're going to go in a counterclockwise pattern. And so what happens is this warm water comes in, and it ends up being taken northward, right? Here's the Gulf Stream over here. And in doing so, we're basically taking solar energy from the equator, and we're distributing it around the planet. If it weren't for these oceans, the temperature difference between the equator and the mid-latitudes and the poles would just be freakish. It would just be burning hot at the equator. But fortunately, Water's good at absorbing heat energy, and it's moved by these winds. So these currents carry it and redistribute it all over the globe. And so basically what that does is it keeps our planet's temperature moderated and less stratified by latitude than it otherwise would be. All right. And so basically we have warm currents and we have cold currents. So typically the warm currents are along the equator and then on the west side of the ocean basins, equator west side. And then what we find is that on the polar areas, and surprise, surprise, it's colder. And then on the east side of the ocean basins, we tend to have this colder water. Now, let's just look at the Atlantic, okay? So in the Atlantic, we have the Gulf Stream. I just want to point out one that's really important about this is so the Gulf Stream, which is one Benjamin Franklin took, it ends up going way up here towards Norway. And if it wasn't for this, like all this energy from the equator is being brought up here. If it wasn't for this, it would be freezing, freezing colder. There'd be continental glaciers here, but there's not because this current is carrying heat energy up to those far latitudes. Now, there's more than just surface currents, it turns out. There's also bottom currents or density currents. So let's look at how they work. So, and they're mostly a function. The main one is really, I say they, but really it's one, and it's at the North Pole. Because remember, the North Pole doesn't have any continental landmass; it's just ice. And so, what happens is at the North Pole, as ice forms, what happens is the water crystals tend to form, even though it's salt water, it's primarily just H2O that's forming in the ice. There's a little bit of salinity in it, but most of the salt gets excluded from the formation of these ice crystals. So what happens is directly below the ice, we have this very, very cold, very salty water. Well, when you cool water down, it becomes dense. And when you increase its salinity, it becomes dense. So right underneath the forming ice of the polar ice cap, the Arctic ice cap, you have this descending water. Now this diagram doesn't show it very well. It basically goes to the bottom. So it sinks. And it sinks because it's very cold and it's also more salty than the other water around it because the water got taken up into the ice and the salt was left behind. All right. So we get this density current that forms and it goes all the way to the bottom of the ocean. Now, this diagram is, I don't expect you to understand it. I don't understand it, okay? But basically, here's the idea. We have equatorial winds blowing, okay? And they carry warm water up towards the pole, okay? And then what happens is, here at the pole, at the North Pole, you get the sinking cold, salty water. And so what happens is it flows southwards and it moves into different ocean basins and then as it heats up, it floats back to the surface, and then warm water is pushed this way, where that warm water gets up here, it cools off and it sinks. And so we call this the thermal conveyor belt. So, and this conveyor belt takes thousands of years to cycle. All right, it's a very slow, continuous flow of heat energy around the globe that's driven by two factors: the global winds, primarily the Hadley and Farrell cells, and the density currents caused by seawater freezing at the North Pole. But global warming is causing this conveyor belt, this thermal conveyor belt, to slow down for two different reasons. And what's going to happen as a result of this is we should expect that the equatorial water is going to become much, much warmer. As if I'm not moving this water, then it's going to reside at the equator longer, absorbing more water and getting hotter. All right, and then it's going to expand more. We're going to get more sea level rise and so on. Now, as the global warming expands the Farrell cell, what happens is the Farrell cell, remember, it goes from, instead of landing at 30 degrees, it's as the world gets hotter, the Farrell cell convects more and carries this air farther north. So it's got to travel a greater distance back to the equator, and greater distance equates to more friction, so it ends up blowing slower. Well, if it's the trade winds that make the equatorial warm water current, and those trade winds are slowing because of increased friction, because they're going extra 10 degrees, basically, then what happens is that you have a slower equatorial current because you have slower trade winds. And the slowing of the trade winds is very well documented. So as the trade winds are slowing down as a consequence of the expansion of the Hadley cell, then what we get then is a slowing of the equatorial current, and we're moving heat energy out of the equatorial regions at a slower rate. At the same time, glaciers are melting because of global warming. Well, remember, glaciers are fresh water, right? And fresh water, as it flows into the ocean, we're not talking about melting sea ice. We're talking about continental ice from basically from Greenland. And from glaciers in Alaska, whatever. But mostly we're talking about Greenland. As that water comes into the ocean, it's not salty, so it's far less dense than the seawater is flowing into. So fresh water has a tendency to float on top of salt water, and now when that ice forms, it's not forming in the same salinity that it used to. It's in a much reduced salinity environment because of all this inflow of fresh water from the melted glaciers. So as the ice crystals form at the pole, there isn't as much salt in the water to exclude. So I don't get that added salinity density that drives the bottom currents. So between those two things, between having a diminishment of the push of the sinking high salinity water, which is no longer as highly salty as it was, and a diminishment in the speed of the uh, trade winds, which move the equatorial currents, this entire conveyor belt is starting to slow down. And what that does is it completely changes where heat energy is in the world, right? So, and that changes all kinds of weather patterns. And as weather patterns change, productivity of areas change. It leads to desertification in some places, flooding in others. But basically, ecosystems are designed to thrive best in stable, known situations. As you introduce inconsistency, you end up stressing out all of the world's biomes as a consequence of this. And then from a human perspective, just consider this, right? The Gulf Stream, we said, brings all this warm water to northwestern Europe. Well, it's not doing it as much anymore. It's slowed down a lot. It's the weakest it has been in 1,600 years, as far as they can tell. Not from they have geologic records that allow them to make that assertion, but basically, it's slowing down, and it's the slowest it's ever been, as far as we know. And as it continues to slow down, there'll be less and less heat energy delivered up here. And so, one thing that will happen is these areas will get colder. Now, they're close to the poles. Maybe this will produce a negative feedback loop, which would be kind of nice. But right now, it doesn't seem like it's going to be significant enough to counter the effects of global warming's many, many positive feedback loops. Hey, thanks for watching.